And thank you for the invitation and introduction. So what I wanted to say was, since this was work for my PhD, and this is not that top recent, like the work just presented by Ben, this is work from like 2 works we published in 2018 and 19, but I hope you still find the ideas interesting. So let's jump into it. The kind of playground we are working with here is hand pose estimation, which 3D hand pose estimation actually. So this means we are given a depth image of a hand, and we want to train a model to predict the 3D pose of the hand. So this can be described, for example, by the 3D joint positions for each of the joints and some key points. And to learn such a model, what you would usually do, or what the state of the art is doing, is usually to take a lot of, capture a lot of data and label this data, which is of course a lot of effort, because you need to label quite some joints and label them for every image and label those in 3D. And of course, this is a large effort, especially if you need data sets in the range of thousands or millions to get a good accuracy. So the usual case here is an example for hand pose estimation, but this is quite the usual case. You will not be surprised that the more labels you have, the more labeled data you have, the lower your error, the better your accuracy gets. So here in this example for hand pose estimation, state-of-the-art model achieves reasonable results if you go towards 10,000 or to 100,000 examples, labeled examples in this case, of course. And what you can also see, of course, is, which is also quite typical, that the error goes down, or let's say the increase, or in this case, the decrease in error kind of gets lower the more samples you add, which is, of course, interesting to some extent, because at least even if you have to label more and more data to get better accuracy, at some point, you know, okay, it will not help you to label them more. You would be kind of done if it's leveling off at some stage, right? But this, unfortunately, is not the case. So if you look, for example, like at this plot, which I have taken from some work from 2017, which was targeting like image classification, where you already have this kind of rather large data set. I mean, often people are working with ImageNet data, which is 1 million samples, as you probably know. And they were looking at the case, or asking the question, what happens if we add much more samples? Like what if we use 10 million, 100 millions, or even more samples? And what they found was accuracy is not leveling off. Even with 300 million samples, the more data you have, the higher your accuracy gets. And even though, I mean, this plot here is in log scale, so it's linear in log scale, meaning, of course, the increase in accuracy gets lower and lower, but still, it's not leveling off. It's getting better and better, and even if for different tasks, the same thing. So the point I wanted to make is, of course, this is not, on the one hand, not very elegant, considering, like, for example, comparing to us humans, how we learn, or what Ben just talked about, biologically inspired algorithms are usually much more efficient, also in terms of how many samples we would need to learn a new kind of category, a new object. But of course, this is also kind of an issue, like, because of this big effort in labeling, this is an issue especially for small players, like smaller companies or also universities, which are usually not able to put in this effort to kind of do their experiments on similar methods, similar. This is not only not only for the small players, this is an issue also for the big players. And to make this kind of last point in my motivation, I stole a slide from Kapati, because he did his PhD in machine learning, computer vision, and later moved to Tesla, where he's now the director of AI. And on this, with this slide, he was kind of comparing the amount of sleep he lost over models and algorithms versus over data sets. And as a PhD student, as you can see from this sketchy plot, he kind of said most of the time, of course, he was thinking about models and algorithms. But now, as a director of AI at Tesla, it's kind of the other way around. Most time, or the most sleep he's losing is due to data sets. So, and of course, even though he on his level will probably do that much of labeling, but there are obviously a lot of other tasks involved in this kind of data work. So, for example, how to select the data, how to capture proper amount of data, how to select the data to be labeled, which is the most interesting data to be labeled, and how to efficiently label it. So the point is, this is also a big issue for industry, even for the big companies, not only for the kind of small players, as I argued earlier. Coming back to hand pose estimation and our kind of two works we're doing this, I want to present you. With this slide, the main point is that the error on this task obviously decreases over time. So if you see kind of lower errors in the second work we're presenting, this is not because of our contribution essentially. This is because we are just building on kind of the state of the art, and this got better and better. So the numbers are lower. It doesn't mean our contribution, right? So with these two works I'm going to present you, we usually achieved error rates in the kind of the same range, slightly better, slightly worse than the baselines or the state of the art at this time. But while the state of the art was kind of using the whole, for this example data set, which I don't know, about 80,000 samples, they were always using the whole data set to achieve these results. While for the first work I'm going to present you, which is exploiting unlabeled data, we were able to achieve these similar results with about 1% of the labeled samples state of the art needed. And for the second approach I'm going to present you afterwards is we even made it to achieve similar results with only 0.1% of the labeled samples by exploiting this idea of how to exploit unlabeled data, but also additionally exploiting synthetic data in this case. Let me just jump right into the first part of the work, which is how to exploit unlabeled data for this task, or our idea to exploit unlabeled data for this task of 3D hand pose estimation. And for this, we were exploiting multiple views, at least during training. So we capture the hand simultaneously from, in this case, from two views. So that at the same time, we have an image from each of the two cameras. And the kind of observation we find here, or which we can exploit to make use of this data without labels, is that if you know the pose, you can kind of imagine how the image or how the hand would look from any kind of viewpoint. So if I give you two other images of hands, two other hand poses, you can probably imagine already how this kind of hand poses, how these images would look from the other viewpoint. Here another example, since you now already kind of know this, the relation between the two viewpoints, you can probably imagine how it looks from this other point. So the observation is kind of, the pose is predictive for the appearance of the hand from any viewpoint. As simple as that. And how we are going to exploit it, I will describe in a minute. So just repeating the observation, if you know the pose, like in this case, you can imagine how the hand would look from U1 in this case. But of course, for our approach, we don't know the pose. I mean, we want to exploit unlabeled data. So for the training, we don't want to assume to know the poses. So we don't know them for this illustration. But what we can easily do is we can capture a second viewpoint, right? And we are going to exploit this by, from the first image, so given one image, an image from one view, we are predicting a pose and shape representation, which is essentially a latent representation at this stage. We don't know what it actually is. It's just an unknown kind of pose and shape representation. And given this unknown representation, latent representation, we are predicting the second view. And from this second view, we can easily derive feedback, right? A loss function on the second view. We just need to capture the second view. We don't need to have any labeled data. So we can just backpropagate then our loss from second view to the pose and shape representation and to the first model, which we actually want to train. And based on our observation, if this prediction, this second model would only work if the pose and shape representation would be appropriate. So the idea is if this pose and shape representation is, or if we predicted from using the first model, predicted a reasonable pose and shape representation, then we can predict from this pose and shape representation any other view, any other known view. The pose is predictive for the image or the appearance of the hand of any view. So if you know the pose, you can kind of imagine how the hand would look from any known viewpoint. So in formal terms, a pose representation theta. So if we have a kind of mapping G, which maps the pose representation theta to an image from U1. So this is kind of describing the observation, kind of this, the pose is predictive for the image of any known view. But of course, on the other hand, what we actually want is to predict the pose representation. So we want to learn a function which maps, given an input image from one view, learns or predicts the pose representation. And now, what kind of the model we are kind of exploiting, the idea we are exploiting is can be seen by simply kind of substituting the pose representation theta in the first equation by the second equation, and then we are ending already up with our full model, which is mapping from an image of one view from the hand image from one camera view to the image of another camera view, J. So mapping this image first to a latent representation and then to the other view. But with this whole model, we already got kind of rid of the pose representation, as you can see. So for the whole model, we don't need any supervision of the pose representation anymore. And the objective is just to find this mapping from one view to the other. Okay. But of course, since this is a kind of a latent representation, similar to what Ben used before to investigate this kind of latent representation, since we cannot like investigate this in the same way as we would do for a kind of supervised learning approach, where we check the pose, the distance in the pose space, something like this. What is often done is to find kind of nearest neighbors in the latent space. And if we do this, like if we look at the latent space for some query examples and search for the nearest neighbors in this latent space, what we find is samples which appear quite close in terms of the pose. They're not exactly the same, but they're quite close in terms of the pose. And if you compare these results to the results of which you get with autoencoders is actually rather prominent and rather similar model to ours, because what you're doing is just kind of try to reconstruct the input instead of predicting a different view, is that for this autoencoded latent space, the kind of nearest neighbors you find are not that similar. I mean, they're similar maybe in some respect, but not in terms of the pose. Sometimes it is, but often it is not. Comparing to the results from our model, they're quite significantly closer to the pose of the query samples. So this was kind of the model trained only with unlabeled data, using such a reconstruction loss, a simple reconstruction loss, where you kind of just, I mean, what we used in the end was just a L1 loss to minimize the distance between the predicted appearance from this second model and the ground truth, the captured hand from the other viewpoint. But in the end, of course, you want to do it, or at least in our work, we wanted to exploit this to train a model for pose estimation. So the idea here is that if this is already, like the latent representation theta is already rather specific representation, or is already rather specific to the pose, a good pose representation, then we would also only need a rather simple mapping to map from this pose representation to the final 3D joint positions. And the good thing with this is that to train this rather simple model, the idea is that you don't need that many labeled samples to train this simple model, just to map from this pose representation to the 3D joint positions. And then, of course, we can train this all together in a kind of semi-supervised fashion, and by just combining these two losses together. And what we find using this kind of semi-supervised model is that, or maybe first the supervised, so this plot is just showing the results for a supervised model, where you see that for a low number of samples, you got a quite high error, and it's kind of steeply going down towards a lower error when adding more and more samples. But comparing to our semi-supervised approach, where we jointly train with labeled and unlabeled data, we can significantly decrease the error, especially for the cases where we have a low number of samples compared to the supervised case. So this was it for how we exploiting unlabeled data. But as the one issue with this approach, maybe I should just go back, is of course that still you need some labeled data to achieve a reasonable accuracy. As you can see from the plots, you still have this kind of behavior that the more labels you add, the better your error gets. This is still the case, and this is of course because you still need to need labeled samples to train this kind of second model, even though it's like the second head to predict, to map from the latent representation to the 3D pose, to the 3D joint positions in this case. So you still need labeled samples to train this model, even though it's a smaller kind of head. And for the kind of second work, we wanted to exploit synthetic data for this to improve on that. So synthetic data is obviously available for numerous applications, like for semantic segmentation, for optical flow, depth estimation, and so on. But of course, we have one big issue here. This is the domain gap. So the synthetic data, if you compare synthetic images with real images, you can clearly see a gap in the distributions. So since for our task of hand-pose estimation, we kind of have corresponding samples from synthetic data, so synthetic samples which are corresponding to real samples in terms of the pose, like you can see here on this slide, and you can clearly see the domain gap, the noise you don't have in the synthetic data. So this is of course usually an issue when you train these models. And looking at a visualization of the feature space, if you train such a model with only synthetic data, so like assuming that you could just use synthetic data to solve this task and train a model using only synthetic data, and then we were here visualizing the feature space with corresponding real and synthetic samples. So each of the kind of orange dots represents a synthetic sample in the feature space, and the green dots represent real samples, and those samples, so each of the orange dots is exactly corresponding to one green dot. But as you can see in this latent space kind of visualization, these corresponding samples are not quite close together, or only in some cases they are close together. So this already kind of indicates this domain gap in the latent space, which of course is an issue if you want to exploit synthetic data for generalization on real data. So this is kind of this basic setup. Maybe I'll just describe what we are doing here. So we train a model with real and synthetic data, and the set is now representing this kind of latent representation, for which we of course have this kind of domain gap, even though we have a corresponding real and synthetic sample, the latent space representation will likely be quite different, right? So what we want to do is to bring those latent representations close together for samples which represent the same pose. So we kind of wanted to map from the latent representation of real samples to the latent representation of synthetic samples. And then from this map to the final pose representation. The idea being that in this way we can exploit all the synthetic data we have for this final mapping to the pose representation, for which we still need label samples. But of course, I mean, if we do it that way, we are kind of assuming that we know, like, if we want to minimize this distance after the mapping, if we want to minimize the distance between synthetic and real samples, what other works are, for example, doing is assuming that they know the correspondence between real and synthetic samples, and then just minimizing this distance in the latent space. But of course, if you're assuming that you know the correspondence, you're kind of assuming that you know the pose also of the real samples, because if you want to have a corresponding real sample to a synthetic sample, you would need to know the pose of the real sample. So the question for this work was how to train this mapping without having corresponding samples or without having labels actually for the real data. And this goes back to we exploit kind of two ideas for this, and one, of course, being this, as I already said, this idea I introduced earlier for enforcing this pose specificity based on this observation we made earlier to kind of train a mapping from one view to the other. But of course, what can still happen is, even though like using this idea from before for exploiting unlabeled data, where we showed that the latent representation is quite specific to the pose, so similar poses are close together in the latent space. What can still happen is that similar poses are close together in the latent space for real samples and for synthetic samples, but kind of separately, because the model just finds it easier to kind of predict real samples separately from synthetic samples, because the domain gap is that big. So to overcome this, we exploit some ideas from adversarial training to kind of try to enforce the distributions to be aligned in the end. So the one loss kind of, we add two kind of heads, and the one head I already described earlier, like we use this kind of view prediction idea to exploit unlabeled data to predict how the real samples and also synthetic samples would look from different viewpoints. And then we also add a kind of a discriminator, a critic, to predict whether this sample is real or synthetic from this latent representation. So this critic only gets the latent representation and aims to this, so its target is to discriminate real and synthetic samples. And then we use this kind of this idea of adversarial training to train this mapping to kind of fool this discriminator, so that the mapping now, the target for the mapping is now to make these distributions of real and synthetic samples in the latent space indistinguishable from each other, kind of fool this critic. That's kind of straightforward application of the idea of adversarial training. Yeah, already coming to some results. So what you can see is the kind of case when we only train with real samples is, of course, as I showed kind of in the very beginning, that if you have a low number of samples, you're completely off. Your error is pretty high. You really need a high number of samples to get a reasonable accuracy. Then if you only have synthetic samples, of course, this, since I'm always drawing this as a number, so that the error as a number of as a function of the number of labeled real samples, sorry, this is kind of constant, but you're still not getting very satisfying results in the end. If you combine real and synthetic samples, so straightforwardly, you're already improving on both of these works. But but we could show that if we are kind of adding up each of our kind of heads or each of our losses, like the distribution matching or the view prediction loss, we can improve on that quite a bit. Each of them separately improves with that, and combining all together again improves the results a bit in terms of the numbers. So in terms of this latent representation, latent space visualization I showed you earlier, now after training with those two additional losses, what we can see is that the real and synthetic samples, corresponding real and synthetic samples, are getting quite close together in this latent representation. And finally, or maybe the second last result I wanted to show you is some qualitative results where we're kind of investigating where does this unlabeled data especially help. And what we find is that maybe unsurprisingly, it exactly helps in cases where there are a lot of distortions. So here you see two samples, the ground truth on the left, if you train only with labeled in the middle, and then our approach training with labeled and unlabeled together. So we only use 100 labeled samples in this case, and the rest unlabeled. We can get a significant improvement also in this kind of qualitative results for exactly these cases where there are a lot of distortions, so where the domain gap is rather big. So for this, overcoming this domain gap, this unlabeled data is quite important. And finally, just some videos. Okay, I cannot show this. Sorry. Now being on this machine, I cannot show you the videos. So I have to skip this. Sorry for that. I'm just wrapping up what I told you, what I kind of tried to convey. So that first, I presented an approach to exploit unlabeled data for learning a post-specific representation without requiring any labeled samples. And we could show that this improves the model, also training it jointly together with labeled data in a semi-supervised approach. We could show that this improves the results by quite a bit. But in the end, of course, we still need some labeled data to train this kind of mapping from this post-specific latent representation to the final 3D poses. So that's why in the second part, we exploited synthetic data to map from the kind of the latent representation of real samples to the latent representation of synthetic samples, and exploit the synthetic data to train this final mapping very accurately. And in this case, we could kind of improve the baseline with only like 0.1% of the labeled real samples, which was used by the baseline or by the other works, by state of the art at that time. Finally, since this was like two works from my PhD, I of course have to thank many collaborators or just discussion partners which helped me and supported me during this time. So putting down some of my collaborators have put down some photos of my collaborators on this slide. So thank you for your attention, and I hope it was still interesting, even though not top recent work, still some interesting ideas for you.